Hello everyone, this is Dr. Ranjith Kumar Gatla, working as an Associate Professor in Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about the classification of elements. So, some part of this topic, classification of elements, we have already covered in the previous class, in the previous video. So, in this video, I'm just continuing the classification of the elements. So in the previous class, we have discussed the different classification of the elements. Okay. So in that majorly we have discussed about the active elements. So in the active elements, again like independent source and dependent source, and again in dependent and independent source, we have also discussed like ideal source and practical source. So majorly the two different types of active sources are voltage source and the current source. Okay. So in today's class, we are going to discuss about passive elements. Okay. So active elements, as we discussed in the previous class, active elements is nothing but those are the energy supplying elements. Okay. Those are the energy supplying elements like voltage source and the current source. And when coming to the passive elements, the elements which consume energy either by absorbing or by storing are called the passive elements. Okay. So the exact opposite to the active elements. Active elements are energy supplying elements. Okay. These are energy consuming elements. Okay. The consumption, either it may be absorbing or it may be storing. Okay. In any way, it is these elements are the passive elements are nothing but the energy consuming elements, okay, is called the passive elements. And some of the examples of the passive elements are resistor, inductor and the capacitor. Because in this course, majorly we are analyzing the circuits, okay, which consist of resistors, inductors and capacitors, and majorly only the resistors, right? Then here, as we know, this is the physical how the resistor physically it's look like. Okay, so not only in this form, there are different types of resistors also there, but the very popular physical looking physical appearance of the resistor is like this. Okay, and this is the inductor and this is the capacitor, right? So these are the the passive elements. So the energy consuming elements, right? And then the another classification is linear and non-linear elements. Okay. So the linear elements is nothing but, okay, a circuit is said to be linear if it satisfies the relation between the voltage and current, which means, suppose let us consider here the examples are resistor, inductor and capacitor. Okay. So the resistor, the current will flowing through the resistor and we can find the voltage across the resistor, right? So which means if the components present in the circuit or the circuit satisfy the linearity, which means the ohmic law, then those kind of elements are called the linear elements. The best example for the linear elements are resistor, inductor and capacitor. Okay, which means the parameters of the resistor, inductor and capacitor other than the resistance, inductance and capacitance, voltage and current is there. So if the relation between the voltage and current is linear, then those kind of elements are called the linear elements. Then when coming to the non-linear elements, if the elements does not satisfy the Ohm's law relation, then those kind of elements are called the non-linear elements. And the best example for the non-linear elements are diodes, transistors and thermistors. Okay, so the diode is very familiar semiconductor device because the diode does not follow or does not satisfy the ohmic law or the Ohm's law. So that's why these kind of elements are called the non-linear elements, which means the voltage is not directly proportional to the current in case of diode. So that's why these are the non-linear elements. So now it is clear the difference between the linear and the non-linear elements. The same way the linear and non-linear circuit is also same. Okay. So if the elements present in the circuit satisfy the Ohm's law, then that kind of circuit is called a linear circuit. If the elements of the circuit does not satisfy the Ohm's law, then those kind of circuits are called the non-linear circuits. So these are the best examples for the linear and non-linear circuits. And then unilateral and the bilateral elements. Okay, so the unilateral means the conduction of the current is only in one direction. Okay, so the conduction of current is one direction is termed as a unilateral element, which means here the best example is again diode and transistor. So let us consider diode. So as we know, the diode symbol. Okay, so the diode will allow the current flow only in the forward direction, which means only in this direction. Okay, so the diode will not allow the current flow in the reverse bias, which means the diode will not conduct in the reverse bias, which means it does not allow the current in this reverse direction. Okay, so the current will allow only in one direction, which means the conduction of the current in one direction. Okay, so those kind of elements are called the unilateral elements, and the best example for these unilateral elements is the diode and the transistor. So okay, so mostly many semiconductor devices, but not all, because again there is a semiconductor device triarc, right? So the triarc can allow the current flow through both the directions. Okay, it will conduct in both directions. So that's why some semiconductor devices are the best examples for the unilateral elements, and those are the diodes and transistors. Then coming to the bilateral elements, the same way, the opposite, because the conduction of the current in both directions in an element, okay, with same magnitude. Okay, again the magnitude is not should not be different. Okay, the conduction of the current in both directions in an element with the same magnitude is termed as a bilateral elements, and the best examples again are the resistor, inductance, and the capacitance. Because let us consider a resistor. Okay, as we know, the symbol of the resistor is like this, A and B. Okay, so the current will flow from A to B and B to A with the same magnitude, which means let us consider here 2 amperes is from A to B, then B to A means we will represent minus 2 amperes. Because in the previous class we have discussed what is mean by positive 2 amperes and negative 2 amperes. Okay, so which means the opposite direction to the reference direction. The minus means the opposite direction to the reference direction. That indicates the minus. Okay, right. So the bilateral elements are nothing but the conduction of the current in both the directions. Okay, with same magnitude, and those kind of elements are called the bilateral elements. And the best example for the bilateral elements are the resistance, inductance, and the capacitance. No, not capacitor. Then the next classification is time variant and time invariant. Even the name itself, it is giving the definition. Okay, so time invariant and time variant. Okay, which means the magnitude or the value of the particular element will not depends on the time. Okay, and if it is depends on the time. Okay, both cases are there. Suppose if it is a time invariant, then the value of the particular element will not depends on the time, which means at every instant of time the value of a particular element is constant. Then those kind of elements are called the time invariant elements. So here as you can see, an element or a system is said to be time invariant if parameters of the element do not vary with time. So for example, let us take a resistor. Okay, so the resistance value of the resistor will not depends on the time. The resistance of the resistor is always same with respect to time. Okay, so it is the value is constant irrespective of the time. So at every instant of the time, the value of the resistor is same. So those kind of elements are called the time invariant elements. Then when coming to the time variant elements, the parameters of the time variant are not constant, because the value of the parameter or the value of the element is changing with respect to the time. If it is changing with respect to the time, then those kind of elements are called the time variant elements. Okay, so which means at every instant of time, the value will change. Because for that best example, okay, let us consider, because this is not only an element are a system. So let us consider the VI characteristics in case of resistor, right? If you are increasing voltage, the current will also increase. Okay, then this curve is not constant with respect to the time. Let us consider time here. Okay, so at every instant of time, here we are changing the voltage and we are changing the current, so that the characteristics will also change. Okay, so which means the parameter or the value of any element is changed with respect with respect to the time. Okay, then those kind of elements are called the time variant elements, right? So this is clear about the time variant and time invariant elements, right? So as you can see here, in the first case, this is the time invariant, because here the magnitude of this voltage is always constant with respect to the time. This is the time axis. Okay, so let us consider T1, T2 and T3. So at every instant, the magnitude of the voltage is constant. So this is the time invariant elements. And when coming to the time variant elements, as you can see here, okay, so at the time, it is changing with respect to the time. These kind of elements are called the time variant elements, right? Then the final classification about the elements is lumped elements and the distributed elements. And the lumped elements means the elements which are physically separable are called the lumped elements. Okay, so which means let us consider a circuit of RLC. Let us consider a circuit of R, L and C. Okay, so this is a RLC circuit. So here the elements, what are the elements? Here it is R, here it is L and C. Okay, so the elements of a circuit which are physically separable. So we can separate resistor and inductor and capacitor separately. Okay, so then these kind of elements are called the lumped elements. Okay, which means these R, L, C, the resistor, inductor, capacitor are the lumped elements. Then what about the distributed elements? The distributed elements means the elements which are physically inseparable are called the distributed elements. Which means the best example is a transmission line. If you take a transmission line, the transmission line having, it consisting of both, it is a combination of resistor, inductor and the capacitor. Okay, but physically we cannot separable, because the transmission line, throughout the transmission line, the resistance, inductance and capacitance are distributed. But we cannot separate the resistor, inductor and capacitor from this transmission line. Okay, so which means physically non-separable. Okay, physically non-separable or unseparable. So that's why those kind of elements are called the distributed elements. So the best example is the transmission line. Transmission line means, the lines which are used to transmit the current from one place to another place. Okay, the electrical energy from one place to another place are called the transmission lines. So this is all about the classification of elements, right? And now we are going to discuss about the passive elements, which are resistor, inductor and the capacitor, and as well as the voltage and current relation in each case, right? So first let us discuss about the resistor. What is meant by the resistor and what is the function of the resistor? So here a resistor is a passive element which is having the two terminal electrical component, that implements electrical resistance as a circuit element, which means it will resist the flow of electrons. What is meant by flow of electrons? Is nothing but the current. So the purpose of the resistor is to oppose the flow of electrons or to oppose the current. So that is the function of the resistor. And the value of the resistor, we will measure in terms of resistance. And the units for the resistance is ohms. So the resistance is nothing but the property of resisting the flow of electrons or resisting the flow of current is called the resistance. And the unit for the resistance, which means how much resistance a particular resistor is having, okay, then we usually measure in terms of ohms. Okay, ohm is the unit of the resistance, and here you can see the symbol of the resistor and how physically the resistor look like. Then if you want to, suppose this is the resistor, if you want to, the resistance of this resistor is depends on the type of the material which you are using, okay, and the area of cross section of this resistor, and also it depends on the length of the resistor. Okay, so that's why you can see R is equal to rho into L by A. Rho means the resistivity of the material, the type of the material which we are using. Okay, and A is the cross sectional area, and L is the length of the the resistor. So the resistance of the resistor will depends on the length, and especially the length and area. Okay, the length and area of the resistor. And usually the resistor symbol is like this. Okay, and we usually represent with a capital letter of R. Of course, sometimes small letter also we usually represent, but mostly capital R. The resistor is represented with the capital R. This is about the resistor. Then what is the voltage and current relation between the relation between the voltage and current in case of the resistance element. Okay, and so here we have already discussed these things in Ohm's law. Okay, so Ohm's law defines at a constant temperature, the voltage across an element is directly proportional to the current flowing through the element. So here, then if you remove the proportionality, then you have to include one constant, and that constant is here called as a resistance. So that's why the voltage and current relation in case of resistance element, so here V is equal to I into R, okay, which is nothing but R is equal to V into I. So which means the voltage across the resistor V is equal to I into R, and the current flowing through the resistor I is equal to V by R. The current flowing through the resistor I is equal to V by R. So here where V is the instantaneous voltage in volts across the resistor, and R is the resistance in ohms, and I is the instantaneous current in amperes flowing through the resistor. So this is the voltage and current, the relation between the voltage and current in case of the resistance. And next we will move into inductor. So an inductor is also called as a coil or choke or the reactor. Okay, so the another name of the inductor is coil, choke or reactor. Of course, the inductor having many functions. Okay, so based on the function, we usually call it as either it is a coil or choke or reactor or an inductor. But the major function of this inductor is, okay, or the major use of the inductor is, it is also a passive element and it is also having the two terminals. Okay, so it stores energy in the form of magnetic field when an electric current flowing through this inductor. When an electric current is flowing through the inductor, it will store the energy in the form of magnetic field. That's why we discussed the passive elements are nothing but the energy consuming elements. Okay, so the consumption means either in the form of absorption or it may be stored. So here the function of the inductor is, because the function of the resistor in that case it is absorbing the energy, but here it is storing the energy, okay, in the form of magnetic field. Okay, so how actually inductor it looks like means, an inductor typically it consists of an insulated wire wound into coil or around a core. Okay, so which means a conductor carrying a wire wound around it, then it is called as an inductor. Okay, so in case of, then how we can measure the value of the inductor means in terms of inductance. Okay, and the units for this inductance is Henry. We usually represent as a H, and there ohms means this is the symbol of ohm, the resistance value. Okay, so in Henry, instead of writing Henry here, we simply write H, capital H, the units for the inductance. And here the value of the inductance is mainly, okay, depends on the number of turns around the coil, the number of turns around the conductor. Okay, so which means L is directly proportional to N. So that's why the inductance value, we usually represent the inductance value is L. Okay, so it is represented like this. This is the symbol of the inductor. Okay, then L is equal to mu into N square into A by L. A is again the area of cross section and L is again the length of the conductor. And N is the number of turns. Okay, the number of turns. So here inductor is nothing but it is a two-terminal passive element, okay, or two-terminal passive electrical component which stores the energy in the form of magnetic field, is called as an inductor. And how to measure the inductor value is in terms of inductance, and the units for the inductance is Henry. And the inductance of a inductor mainly depends on the number of turns. Not only number of turns and length and area of the cross section of that particular conductor also. And the symbol for the inductor is like this. This is about the inductor. Then we will discuss the relation between the voltage and current in case of inductor. So here this is the voltage and current relation between the inductor. Okay, so it is not as simple as like what is that in case of resistor. So here if you want to find the voltage across the inductor, V is equal to L into di by dt. So here di by dt is rate of change of current. Di by dt is nothing but the rate of change of current. And if you apply the integral to both sides, then we can find I. So I is equal to 1 by L into integral V into dt. So here V is voltage across the inductor and L is the inductance of the inductor. Okay, so and di by dt is the instantaneous rate of current or charge. And the major applications of these inductor is we can use this inductor as a filter, and sometimes we can use this inductor as a sensor, and sometimes we can use this inductor as a transformer, because not exactly the inductor we cannot use as a transformer. Okay, but in the transformer also, okay, the same inductor properties it is having, like the coil. Okay, coil is nothing but the inductor. The transformer also having coils, primary and secondary coils. So there is again different concept of mutual inductance. So based on that it will work. And motors and energy storage, etc. These are some major applications of the inductor. Then coming to the capacitor. So the capacitor and inductor function is same, but only the difference here you can see is here the capacitor is also a two-terminal passive component. Okay, and it is also store the energy, but it stores the energy in the form of there in the form of magnetic field. Here it is in the form of electric field. That is the only difference between. But of course, the physical, the internal structure and the the outer shape, both are different for inductor and capacitor. Okay, so here the inductor is consisting of two plates. Okay, and in between two plates there is a placed a material that is called the dielectric material. You can see here the capacitor is made up of two closed conductors, usually plates, and that are separated by a dielectric materials. So which means here let us see, here this is plate 1 and this is plate 2 and in between this is the dielectric material we place in between these two plates. So that's why here the capacitor symbol is like this. Their inductor is nothing but, okay, if you what is that, wound a what is that coil around the conductor, then that is called the inductor. So that's why the symbol is here like this. We are just wound the wire around the coil, and here it is the capacitor, because the capacitor is nothing but the physically, okay, there are two plates. In between these two plates, a dielectric material is present, or that the two plates are separated by a dielectric material. This is called as a capacitor. Okay, and here, of course, if one capacitor is having positive charge, then the second capacitor will have the negative charge, right? And this will measure in terms of the capacitance. This will measure in terms of capacitance, and the unit for the capacitance is Faradays. So we simply represent in terms of F. Okay, and here the C depends on the distance between these two plates. So that's why here C is equal to what is that, E naught A by D. Here A is the area of cross section of the what is that, the plates, and D is the distance between these two plates. D is the distance between the two plates. So here this is about the capacitor. Then we will discuss the relation between the current and voltage in case of the capacitance. So here I is equal to C into dV by dt, and V is equal to 1 by C into integral I into dt, where I is the current flowing through the capacitor, and L is the what is that, the capacitance, sorry, not L, here it is C. It is typographical mistake. So here C is the capacitance in the Faradays, okay, and dV by dt is the rate of change of voltage. So almost the applications of the capacitor is also similar like the what is the inductor, okay, but here the there the inductor applications are like the transformers and what is that, motors, which means the electrical machines. But here, other than the electrical machines, same filters, sensors, and energy storage, etc. These are the applications of the capacitors. So here you can see the various types of what is that, of course in the resistors also there are different types. What is that, the fixed value resistor is there, and variable resistor is there, okay. So like this here, the fixed values are usually what is that, represent like this, because this is the fixed inductor, and this is the fixed what is that, inductors values, fixed inductors values, okay. And these are the iron core which represents this, if the symbol is represented like this, okay. We will discuss later what is mean by the iron core and what is mean by variable, variac, and tap, okay. So these are the different ways to represent the inductor, but in this course we mostly use only either this representation or this representation. Only these two representations we will use in this course. And again in the resistor also, this is the fixed value of resistor, and if it is a variable resistor, then we usually indicate like this, okay. The same way variable inductor also, or variable capacitor also, because if it is a constant, then simply this is inductor and this is, oh sorry, this is resistor and this is inductor and this is capacitor, R, L, C. This is the, if it is a fixed value, then it is represent like this, and if it is variable, then just an arrow, which means this is variable in resistor, variable inductor, and variable capacitors, okay. So here the physical appearance of the resistors are like this, 1 and 2. You can see in the laboratory, electrical circuits laboratory, you can find, but mostly we use these kind of what is that, resistors only we use in the laboratory, okay. And even the inductors also, as you can see, various types of inductors, which means the coils, okay. And these are also, this is in a transformer, okay. So how the coils are placed, okay. So similarly, this is the fixed constant capacitor, and this is the variable capacitor, and these are the physical how physically the capacitors are look like. Of course, it is depends on the, again, there are various different types of capacitors are there, and again, what is that, based on the value of the capacitor or the size of the capacitor also, here the, what is that, the physical appearance will change. And when coming to the standard symbols of the electrical component, okay, so these are very important. Already we have discussed some standard symbols, which means how the voltage source will represent and how the current source will represent and how the resistance will represent, okay, how the inductor will represent and how the capacitor will represent. The standard symbols already we have discussed some more. Here, this is the DC voltage source representation. Sometimes you may find the same voltage source representation like this also. This is also fine. This is also a DC voltage source representation. And in case of AC, you can see inside the circle, you will just have a small sign symbol. Okay. And this is the DC current source and this is the AC current source symbol. These are the voltage sources and these are the current sources symbol. Okay. And this is a meter, this is voltmeter, and this is the ground, the symbol. Okay. And battery we usually represent like this. Okay. So one and a small plate and like this. Okay. So this is the battery representation. Okay. Switch. This is the switch representation. If you close this, then it is on position. If it is open, then it is the off position. And this is the diode representation, as you know already. And this is the transistor representation. Of course, PNP and NPN, just what is that? The terminals are changed, but physically the PNP and NPN transistors are looks like same. And this is the similar symbol of the light emitting diode. So these are the basic symbols of the electrical components. So this is all about what is that? The basic definitions and the basic classification of elements. Okay. And the basic laws, not laws, the basic law, which is Ohm's law, which is associated with this, what is that, the basic electrical elements. So in the next class, we will discuss the further topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.